Well, today we're talking about magnetism in the context of transition metal complexes. So unpaired electrons in any molecules interact with magnetic fields. So if you have a transition metal complex and you want to know whether it's high spin or low spin, the difference tends to show up in how those compounds will interact in what's called a GUI balance that can measure the interaction with a magnetic field. And because it's the unpaired electrons that are interacting with the magnetic field, the more unpaired electrons there are, the stronger that interaction with the magnetic field. So if you've got a high spin complex, magnesium 2+, you'll have more unpaired electrons. It'll interact more strongly with the magnetic field than a low spin complex will. The parameter we get out of that measurement is called magnetic susceptibility. It's given the symbol μF or mu effective. One of the useful things about it is that it can be directly compared to a simple mathematical prediction called mu-SO. SO is for spin only. And that looks like this. mu-SO equals the square root of n into n to plus 1, where n is the number of unpaired electrons. Now, there's a shortcut for that calculation. The calculation is pretty simple in the first place, but there's a shortcut that makes it even faster. Of course, when n is equal to 0, then mu is going to be 0. There are no unpaired electrons to interact with the magnetic field. But if n is any other number, and remember, we're talking about transition metal complexes, so we're really talking about anywhere between 0 and 5 unpaired electrons, then the mu-SO value is, if we round up on that calculation, is going to be the number of unpaired electrons plus 1. So it's pretty easy. If we have 2 unpaired electrons, we'd expect a mu-SO of a little bit under 3. If we have 4 unpaired electrons, we'd expect a mu-SO a little bit under 4 Bohr magnetons. And that symbol mu-B is Bohr magnetons. It's the unit of magnetic susceptibility. We can also use these measurements to compare 2 different possible geometries. So for instance, if we think something's going to be tetrahedral versus square planar, those 2 possibilities might give us different magnetic susceptibilities. In the case of nickel 2+, if it's tetrahedral, we'd have 2 unpaired electrons and we'd expect a mu-SO of a little bit under 3 Bohr magnetons. And if it were square planar, we'd expect magnetic susceptibility of 0. So we can determine, using magnetic susceptibility, whether something is high spin or low spin, and sometimes what geometry the complex is in, just by comparing the measured magnetic susceptibility, mu effective, to the predicted magnetic susceptibility, mu-SO.